All right, so tonight we're going to carry on with chapter 9. So we're ready for section 9.4. And for the next few sections, we'll continue to look at different techniques for determining if a series is either divergent or convergent. And, there's a lot of different cases we could potentially run into. So that's why this is a very complex subject that we're diving into here. So we'll start with the comparisons of series. And what we're looking at here is two tests here, the direct comparison test and the limit comparison test. And, so at some point, what'll start to happen is you'll look at all these different series that you're trying to think if they are convergent or divergent. And of course, the first step will be to think of which test is the most appropriate. And so somewhere along the way, they do have a nice little chart here that'll help us keep track of it all because, there's a lot of information to remember when we try to apply these different tests. In each case, there's different assumptions that we're making and different conditions that have to be met. So, and the results have to be determined properly. So there's a lot going on here. So we just want to understand each of these tests individually. And then at some point, we want to examine that chart to help us understand how to know when to use which of these tests. All right. So they're making the point here that, the tests we've seen so far have been based on the assumption that the series had a certain pattern to them. There was some kind of a very obvious formula that we could follow. And they're also saying here that, even subtle differences can throw off our ability to use different tests. So here's an example of what they're talking about. Now, here you've got 1 over 2 to the n. And if you remember from way back, this is a geometric series. Actually, let me make sure I'm using the exact same notation. Nope, I knew it. They're using n. Every math book is a little different. So let's make sure that everything's consistent. So we're starting at 0, going out to infinity. And you might recall that this one has a very nice solution. As long as the absolute value of r is strictly less than 1, then this sum is equal to a over 1 minus r. It couldn't be any simpler. Okay, but that requires the absolute value of r to be strictly less than 1. Otherwise, the series diverges, which means it's going to get explosively larger small. And so they want you to notice that this one that they're showing us in this first example, 1 over 2 to the n is the same thing as which means that, of course, that a is 1 and r is 1/2. And since r is less than 1 in absolute terms, that means that this series not only converges, but we know what the sum is. That would be 1 over 1 minus 1/2, which is 1 over 1/2, which is 2. But unfortunately, if we instead have n over 2 to the n, then clearly that's a different case altogether. All right. And so they're saying that superficially they look very similar, but the reality is they're very different as far as these tests are concerned. And then here, you might recall that we defined this type of setup as a p-series. So we have 1 over n cubed and you recall that for this type of series, that 3, by the way, is the p. So in other words, and so if you remember from that section, the cutoff point here is 1. Okay, in other words, if n is greater than or equal to 1, or actually strictly greater than 1, then the series converges. Oh, sorry, it's not n, it's p. It's p that we're comparing with. N is the index, p. But of course, anything below that, between 0 and 1, diverges. Okay, now the one right next to it, um, 1 over n cubed plus 1 is not a p series, so we can't use the same type of test to determine if it's divergent or not. Okay, then in the last case, I guess they want you to see that, if you're thinking about using the integral test, that the one on the left, it would be much easier than the one on the right. Okay, the one on the right is just a little bit messier. So actually, I'll tell you what, let's go back and find where the features, I think it was the last section, 9.3, where they introduced the P section, P series rather. Hold on. Just to make sure you remember where you can find this information. That's what I thought. All right, let's go back and revisit it real fast. So this is what they're directly referring to, the convergence, the integral test. We can test convergence with an integral that corresponds to our series. And but even here, if remember, there's quite a few requirements. We must have f is positive and continuous but decreasing for all x greater than or equal to 1. And but here, the p series, if you notice 1 over n to the p, no matter what p is, as long as it is strictly greater than 1, then this series converges to some constant. Anything between 0 and 1, well, we end up with a divergent series. Okay. Okay, so then let's get back to 9.4. Now, direct comparison. So sometimes what will happen is the only option you really have is to take your series and compare it to something else where we can make statements such as a one series is always greater than the other on a term by term basis, or one diverges, is known to diverge, and that kind of thing. And so the larger the 2n, if we know that it converges, that implies that an also converges. So we may have a very messy an expression that we don't want to deal with directly, but if we can find a bn that we do understand very well, and if we're lucky and bn converges, that means that we don't have to worry so much about an because we know that it also converges. But of course, that means we have to prove that all the b terms are greater than or equal to the a terms. Otherwise, this doesn't work. On the other hand, if the smaller the a diverges, that guarantees that b diverges. Okay, so that way, sometimes we may find ourselves needing to find another series that we can work with instead of directly working with the original series. For example, now here, we've got this case, which clearly does not fall into one of the categories we just looked at. All right, but what we can do is find one that we know whether it's divergent or convergent, and that would be the p series. Hold on. All right, and that would be the p series 1 over 3 to the yes. I've got all these YouTube channels open up here. So we can rewrite this as it wants to go there, doesn't it? Okay. Now, what we do know is that, well, actually, I'm sorry, this is not a P series. This is just a regular geometric series because this is R 1/3 and A is 1. Okay. So we already know that because R is strictly less than 1, that means this series is known to converge. And furthermore, we can figure out what it converges to. And that's going to be 1 over 1 minus the third, which is 3/2. Okay. Anyway, the bottom line is it converges. Now, if you look at this term here, or this series rather, because we get that extra term in the denominator, it should be clear that no matter what term we're looking at, it's not going to exceed the corresponding term in the 1/3n expression, right? The sum here. And remember, let's go back and look at our rule here. So that means we're looking at this case here. Number one, if the larger of the two converges, then the smaller also converges. So think of this as the Bn, An. And so therefore, according to this, since we know that Bn converges, so knowing these two things tells me that An also converges. And that's the 1/2 plus 3 to the n converges. Okay. So this is how this technique works, the direct comparison test. And you can see now they went ahead and drew these for us. The blue one, as I already mentioned, we already know it converges to 2/3. Actually, wait a minute. Wait, hold on a second. The diagram doesn't look right. It's 1/3 to the n. 1/1 minus 1/3 is 1/2/3, which is 3/2. Huh. That's strange. All right. Well, we'll worry about that later, but we know that it converges. And now the limit comparison test. Basically what it's telling us is that we have two series. The limit, if the limit of their ratio is L, which is some finite positive constant, then either both of these series converges or both of them diverge. It's not going to be possible for it to be one or the other. Now here, if you remember when they first introduced the P series test in the last section, let's go back and visit that real fast. They did make the point here that the harmonic series is the special case of a P series where P equals 1, and that it can be written in the following form. Okay, that would be the what it looks like. So what they want us to do here is show that between these two, it should be pretty clear, as long as A is positive and B is positive, that 1/n is always greater than this expression. Right, this one, yes, and this is, of course, a P series. But remember, this is the P series where we know that it diverges since P equals 1. This series diverges. All right, and that's going back to the last section. 1 over n to the P, in our case, P is 1. And according to this, that makes it a divergent sequence, a series. All right. But as far as these two are concerned, what we need to know is, does the ratio have some specific constant as a limit? So what we can do is check this out. So now what they're going to have us do is, well, they're going to have us use this in the numerator and this one in the denominator. It doesn't explicitly say if one of them needs to be in the numerator or one in the denominator. It just says if the ratio gives us a constant, then we're good. All right, so let's try that. So we're going to put this in the numerator and this in the denominator. Let's try that. Yeah. Let me copy that out of here so I don't make a typo. All right, so this is what we're after. So we've got one over an plus b over 1 over n. Okay. So when n goes to infinity, oh, I see what they did. Okay, so they rewrote it as right. In other words, dividing by 1 over n is the same thing as multiplying by n over 1. So we ultimately end up with this. Now, the way it's written now, the limit will end up giving us infinity over infinity. So what we can do is divide out all the terms by n. And so this goes to 0. We also end up with 1 over a. All right. Now, what they're telling us here is that given that we have this constant, 1 over a, that means either they both diverge or converge. Now, the one we do know, the P series diverges. And so this result tells me that since 1 over n diverges, that implies that this expression AB plus n also diverges. So they both diverge. Okay. In other words, it has to be both. They can't either. We can't have a mixture. It's either they both converge or they both diverge. Okay, great. And then here they're going to show some quick examples. Now, if you notice, all three of these on the right are P series. Okay. So here the P is 2, which means it converges. Here the P is 1/2, which means it diverges. And here the P is 3. But of course, it's understood that what they've done is they've taken the limit of the ratio and they found a constant. Right? They didn't mention that here, but that's what they've done. And so therefore, you can see that in the first case, they both converge. In the second case, they both diverge. And in the third case, they both converge. All right, so here's an example. I guess they didn't do that one already. All right, here we go. So that we've divided and they've reduced it. Now, they basically, well, they got rid of the plus one. Um, it won't affect the limit. So if you do that, you'll end up with 1 over n to the 3 halves. That means it's a p series. P is greater than 1. That means it will converge. Okay. So yeah, here's where they showed you what they actually did. The full formal definition, they took radical n over n squared plus 1 divided by n to the 3 halves, and this is the final result. So the mere fact that we've got a constant as our limit means that we know that both of them have to converge. All right. So now for something like this, I guess we'll use the approach we had earlier. We're going to take the limit. Uh, they, let's see. Let's see, what can we compare this with? I think that what they intend for us to do here is compare it with um, let's try 2 to the n over 8 to the n, which we know because actually, let me move this real fast. Okay, so yeah, I think we're in the right track. Now, of course, we know that this one converges because we have a geometric series where r is strictly less than 1 in absolute terms. So that means the ratio of these two. So if I divide everything through by 8 to the n, okay, so in other words, this just says that this one converges. All right, so that was knowledge check number 1. All right, so I started to think what knowledge check number 2 is. Oh, wait a minute, wait. All right, well, this one has a square in it. So I think, let's see, what do they want us to compare this with? Let's copy this. So I guess we should compare it with 9 over n, 9n over 9n squared, which is the same thing as 1 over n, which we know diverges because it's a p-series where p equals 1. So the limit uh, as n goes to infinity. I'll tell you, let's just to keep it simple, I'm going to rewrite this in the original form. I think it'll just be cleaner that way. All right, equals. Divide through everything by 9n squared. All right. There's probably at 1, which is different from 0. So our conclusion is that both uh, this and this diverge. Okay, they both diverge. Okay. Yes. All right. Great. So that was 9.4. What new tests are they going to bring us in 9.5? It's going to be a while before we're done with all these tests, by the way. Once we are, though, we're going to get into some very, very deep waters. We're going to introduce Taylor series approximations of polynomials. And so that's going to be a hugely important topic. So 9.5 is, here we go, alternating series. So alternating means they mean alternating in sign. All right. So here, for example, instead of having 1 plus 1/2 plus a quarter plus an eighth plus a 16th, et cetera, every other term is negative. Now, the way they get this done is to have -1 to the nth power, so that, of course, when n is 0, this is just 1. When n is 1, this is -1. N is 2, this is +1. And it just alternates back and forth between the two. And that's what accounts for the fact that these terms, every other one is positive, every other one is negative. So, and in this particular case, it's r is -1/2. Okay, so in other words, oh, right. Because if you have, yeah, because you've got 1 times -1/2 to the 0 plus 1 times -1/2 to the first plus 1 times -1/2 squared. et cetera, et cetera. So yes, that's correct. It's a geometric series where R is negative one half and A is one. So, and now there's two different ways we could have this. In this case, in the left, of course, every other term is negative, but it starts negative. In the one on the right, every other term is negative, but it starts positive. So, as long as an mean every term is strictly positive, um, these two alternating series will converge when two different things are true. Number one, the limit of the nth term is zero, and that's always been true. But then we also require here that now, what does this tell me? Let's try to reason this out for a minute. This is a shorthand way of saying that no matter what n is, let's say a2 is less than or equal to a1. So in other words, you could think of it like this. It might be easier to write it out like this. I think it makes more sense, but I mean, this is how it's formally written. So in other words, the terms of the series are declining. Then that means that these two series do in fact converge. By the way, if these were increasing, it means that the thing is growing without bounds. The series, that is, you can't have a bunch of larger and larger terms adding up to a constant. It's going to add up eventually to infinity. All right, let's try this one. Now, this is one. Now, if you notice, by the way, you have to keep your eyes on this. Sometimes they start these with one, and sometimes they start them with zero. So this one is starting with one. So what is this? Sometimes it's helpful to write out some of the terms so you can visualize what's going on. So the first term, if you notice, n plus 1 is 2. So we're going to have positive 1 over 1. Then you're going to have negative 1 over 2. Positive 1 over 3. Negative 1 over 4. Excellent. Okay. Now, we know that 1 over n converges. Diverges. Okay, so all right, we're not using that test anymore. What we do know is that the alternating series have a limit. Now, there's clearly a limit of zero as we get closer, as n gets bigger and bigger. Clearly, these terms are getting smaller. So the limit of the nth term is zero. So we're good there. And then you can see each term is progressively smaller than the one before it. Therefore, it must be the case that the series converges because we need these two conditions to converge. The limit of the nth term is zero, meaning that the terms are getting smaller and smaller. Well, actually, both of these are telling us that, but here it specifically says that the limit is zero. And then it converges because it means that we will get a sum of some kind at the end, which is not infinite. Oh no, what happened here? It says here the limit. Now you can see the problem here is that the terms are not getting smaller. Or the limit, actually the limit is not zero. Okay, that's what the holdup is here. So in other words, what they're saying here is that you cannot apply the alternating series test at all. Okay, the first condition is that the limit as n goes to infinity as an is 0, which is not happening here. In fact, if you want to check it out, if you just keep writing them out, you'll see they're not getting any smaller. Um, anyway, now this one, wow, it's hard to tell by looking at this one. It says here this one fails the second condition, which is that right. The magnitudes are not getting smaller. So forget this one too. Now, if we do have a series that does satisfy these conditions, then we can at least estimate the value of the remainder term, meaning the part that's only the inaccuracy that we're introducing by adding up a finite number of terms. Okay, so capital N is a finite number. So if we add up only n of the terms, we're going to get an approximation to what the sum of the entire series is. And so what this Rn represents is the remainder, the part that's missing basically by doing it this way. So here we have alternating factorials. And so they're telling us that so this is n across the board. So that would be the expression for each. Let's see, what are they doing there? Let me write this down. It's very confusing the way I read this. We have, now remember, every other one is negative. So we have, let me copy this too. So in other words, what they're basically saying is that like, this one factorial is greater than over 2 factorial, which is in turn greater than over 3, et cetera, et cetera. That's what this means. And it should be clear that the limit as n goes to infinity, if you substitute here, you're going to get a 0. So therefore, that implies convergence. Okay, so in other words, this is telling us that we have convergence. And then if you really need to come up with an approximation, if you notice how we're stopping after 6 terms, and if you fill them in, you'll get approximately 0.63194. And according to this remainder expression, we know that the remainder after 6 terms is less than or equal to A7, which is 1 over 5,040. And that's approximately 0.0002. So the sum is going to be somewhere in between S6 plus and minus the remainder. And that's right here. So if you needed to know the exact value without actually adding up all of them, you could come up with a good approximation. Now, then we do have these different types of convergence. We have something called absolute convergence and conditional convergence. So if the series absolute AN converges, then the series without the absolute value also converges. Fine. So it says here, this converges by the alternating series test. Actually, I think we just did this one, right? Yeah, this one. Okay, we already knew that this one converges. But the harmonic series, meaning the same thing without the signs, diverges. So this one is defined as an alternating harmonic series, and this is just regular harmonic series. And this is a P series, and we already know that when the P is one, that the series diverges. So they're basically telling us that um, without the signs, the series diverges. With the signs, it converges. So therefore, the convergence is defined to be what we call conditional, meaning that it depends on there being signs. Whereas this one, don't have to worry about a thing. All right. The signs are not relevant. The series converges with or without signs. Okay. So yeah, that's what they're telling us. This series is absolutely convergent if the absolute value of those terms converges. The series is conditionally convergent if the original series converges, but the absolute value diverges. All right, so here's some examples. The first one, let's see. Now, they're telling us here that this is an alternating series, right? But if you got rid of the signs, you'd have okay, so it's n factorial over 2 to the n. Should be what, 1 plus 1 half plus plus 6/8. So therefore, so yeah, see what they're getting at is the limit is not 0. Okay. Yeah, because of the way the terms are defined, you can see the first term is 1, then we have half, then we have 2/4, which is a half, 6/8. So yeah, the limit it's not converging to 0. So this one is just divergent. Whereas this one, let's see. Oh, it's a P series where P equals 1/2. Okay, so in other words, the absolute value version does converge, but without the absolute value part and those signs, it would diverge because it would be a P series with P equals 1/2. So that means that this one conditionally converges. Now, this is a very strange idea. Um, in some series, the order in which I add them up makes no difference whatsoever, but in some cases it does. So if the series is absolutely convergent, then it makes no difference what order I write the terms. With conditional convergence, then that's not the case. A different rearrangement might give different results. So here's an example. Okay. Now, of course, what they've explained this very, very poorly, in my opinion, because what will happen is it's not if you just write them in different order, it's the signs that will be affected. So, in other words, if you instead of having this, clearly they're going to have different sums. And then if the series is conditionally convergent, then we can rearrange them to come up with a different sum. Okay. And then here's another one where they're flipping them around. Um, all right, but all right. So what is this? This is 9-5. All right. So 9-6 actually is a little bit more down to earth. These are things you might I think you'll find that these are much more straightforward compared to what we were just doing in 9.5. This one is much more intuitively clear what's happening. So the ratio test looks like this. We have a series that converges absolutely, meaning the signs are irrelevant when the limit of the ratio of consecutive terms in absolute value terms is less than one. If that ratio is greater than one, or it's equal to infinity, to diverge, if it's exactly equal to one, then we have to try something else. All right, so what do we do with this one? So remember, now this is one of the ones that we were unable to do before. Well, actually, it didn't fall into any of the categories is what happened. So what we can do is figure out what the terms are and calculate the ratio of their absolute value, or the absolute value of the ratio, I should say. So if this is an, then a plus 1 will simply be 2 to the n plus 1 over n plus 1 factorial. Oops. So what's the ratio of these two? All right, let's find out. There we are again. All right, so we'll rearrange it a little bit. Okay, now the first one is easy. It's clearly just 2. Now, the second one, we have to be a little careful with this thing because n plus 1 factorial means, well, actually, sorry, it's if it's already plus 1, we subtract 1, this becomes just n. Okay, so in other words, just like factorial is 3 times 2 times 1. So the ratio of these two will be 1 over n factorial. So the ratio then is 2 over n factorial. All right. So let's see. Hmm. Well, obviously it did something wrong. Let's see what's going on here. Should be oh, wait a minute. I know what's wrong. Okay, right here I made a bad substitution. This isn't n plus 1. This is n factorial. All right, let's fix that. All right, let's try that again. Yeah, I copied something wrong. It's two. Yeah, it's fine here. I just copied it wrong. It's 2 to the n over n factorial. And we multiply it out. All right. So if you have a factorial over n plus 1, it would be like having 3 factorial over 4 factorial. So it would just reduce to n plus 1. And now the limit of that as n goes to infinity is 0. And and remember we had became with still there are 3 conditions. Less than 1, greater than 1, et cetera, et cetera. Let's look. Yeah, that would be the first case. Strictly less than 1. So we're good. So that means this converges. Converges absolutely, as a matter of fact. Beautiful. All right. What else? Now the root test. Instead of ratios, we have roots. I mean, that's the name says it all. So if we take the limit of the nth root of an strictly less than 1, it converges. Greater than 1 or infinity is diverges, equal to 1, inconclusive. All right, let's look at this one. So we're going to have the ratio an equals e to the joint over n to the n. So they're going to take the nth root, and that reduces to e squared over n, and that goes to 0. And it's the same thing. It converges because the limit of that square root of that ratio is in fact less than 1. Here we go. Now I think this is where they have the table. Yeah, there we go. There's our table. This table has everything done up to this point. And what they're trying to do is capture all of these results that we've already looked at, that we've been working on for such a long time in one convenient location. Like here's the P series. Remember, when P is strictly greater than one, it converges. When P is less than or equal to one, it diverges. It's a telescoping series, geometric series, the nth term test. So this way, you've got it all right in front of you. You're working on an assignment, let's say, and so. But along the way, yeah, we've got all these other examples here that we should probably look at right now, while it's still fresh in our memories. So we're going to try this one. And let's see. They're asking us to use the nth term test. No, that should be in the chart. Let's see. Huh. Oh, that's right. This is the one. Yeah, this one can only show you if the series converges or diverges rather. Um, so all you're trying to do is show if the limit equals zero or not. All right, it's maybe not the most useful test in the world. Um, so basically what they're saying is to do this. Right? Let's try that. So we take a limit. And of course, what we're going to do is we always do in these cases, divide out everything by n. That's the highest exponent of n that we have here. These two go to zero, left with one third, not equal to zero. And that means that the test, the not so right. That's enough to show divergence. Okay, so that's that one. And they're being very helpful with us here by asking us which test they want us to use. That's really kind of the challenge. But so this series diverges. What's next? Ah, and this is a geometric series. Now sometimes it's just a question of recognizing what kind of series it is. However, it's just a constant. So that means that we can figure out the sum and it therefore converges. Okay, they didn't ask us to figure out the sum, but it does converge. All right, what else do we have? Let's see. Oh, the integral test. All right. Yeah, that's that works well when you have a function that is easy to integrate. So what they're recommending you do is this. The integral test, let's look at the table for a second, is going to be used to integrate from 1 to infinity, the same function, except that it's x. All right, so it looks like this is a job for use substitution. We don't have the -2, but we can provide it ourselves. So whenever there's a constant missing, we can easily supply it ourselves. And of course, we need to rearrange it slightly, just to make it clear that we do have what we're looking for. So this is clearly TU. This is E to the U. All right, so what do we have? All right, E to the U is -x². Now, because that exponent is negative, we're going to wind up with, okay. So in other words, if because e to the -x² is 1 over e to the x², so this just goes to 0. So we ultimately end up with or 1 over 2e. Now, what are we comparing that with? Well, of course, this is positive. And according to this table, the table doesn't even mention it. That seems a little ridiculous. Hmm. See, now I don't remember it saying that. Because this is easily integrated. Oh, no, they're telling us that it converges. Um, I guess we're gonna have to go. The table doesn't have the criteria for determining if it converges or not. I'm gonna have to go back and look it up. I think that was 480. It must have been 3. Yeah, there it is. So, okay, so this one said if f is positive, continuous, and decreasing, then these either both diverge or converge. Okay. So in other words, if it's infinity, it diverges. Okay. So it looks like we're good. So it converges. Okay. Then we have this one. Nth term. Oh, the comparison test. Okay. Yes, it does look a lot like a harmonic series. Okay, so now remember the harmonic series diverges. So remember we had that comparison. Let's go look it up again. It would have been the one right after this 9-4. Yes, here. There it is. This is what we're after. So in this case, with this A and B, this would be A, this would be the B. And since the B, hmm, well, it says here if AN diverges, then BN diverges. So I guess we have to conclude from this that this 1 over 3n plus 1 diverges. Yeah, it does diverge. Okay. Because the harmonic series diverges, so this one diverges as well. What else? Oh, alternating series. Okay. So they've already kind of given it away for us. They're telling us that the limit is 0. Well, that makes sense. If you look at this thing, clearly the limit, because if you divide out the ends, oh, sorry, that would be 4. Just 4. 4 plus 1 over n. That would be 0. Yes. So, and in addition to that, it should be clear that actually, let's copy this into the notes for a second. So we know that the limit is 0. The limit of the nth term is 0. That's not a problem. But what they also require us to do is show this an plus 1 is less than or equal to an. Okay. Or I don't know. I find that very awkward. I'd rather write it like this. But that's the way they've done it. So anyway, an is 3 over n 4n plus 1. which implies that an plus 1 would be five. And clearly, this is a true statement, okay, because we have a larger denominator. So both conditions are met, this piece and the limit. So therefore, it converges. So here they're recommending we use the ratio test. All right, how does, let's see. So if this is our A, um, let's see. Let's go back and look at the list of conditions that we need to meet. Here it is. So the limit, so if this is an plus 1 equals, and that ratio, that's right. Oh, that's interesting. Well, then, okay, hold on a second. Here we go. Yeah, I think what's gonna, I mean, you can see that we ended up with just n. So therefore, the limit is infinity. Oh, that was one of the conditions. I didn't copy that one down, but it was back there. So let's go grab it. It was, no, not that one. There we go. Yeah, this is what we were after. So yeah, it's infinity. I mean, it reduces to n. And when we take the limit as n goes to infinity, we just have an infinity. And that would be this case. And so therefore, this series diverges. Okay. All right. What else do they have? Other possibilities are there? I think we covered everything. So now they're going to ask us to use the root test for this one. So we're going to take the nth root, um, and the ratio. These are the conditions that we need to meet. So we're going to take the limit. We're going to take the nth root of this ratio, We don't have to worry about the absolute value because clearly those are both positive numbers. And the limit, oh, well, the limit here of this expression, we can divide it out by n, which means it's the limit of 1 plus 1 over n divided by 2 plus 1 over n. And since these two both go to 0, we end up with 1/2. And according to this, since that's less than 1, that means this series converges. All right. So, and then the table is next. So I think we've covered every single one of these cases. We're going to be experts by now. And let's see what comes next. So yeah. Oh wait. Oh no, that's okay. All right. And then this is the summary. All right, that's fine. So this is section 9.6. So I was saying before, 9.7 is something completely different. It's our introduction to the concept of Taylor series, which I think you'll find to be extremely interesting. We're actually doing is taking some function or other and approximating it with a polynomial, which comes in very handy in a lot of applied fields. I'll show you some examples we get there. All right, what the heck? I'll show you an example right now. So